Welcome, everybody. So this talk is about building responsible and scalable applications. I have to do the obligatory bio slide, but I'll do it faster. Right, so my name is Jeff Richter, if you don't know that already. I'm a software architect on Microsoft's Azure team. I've been there for about 3.5 years. I've written a bunch of books, the 3 most recent book covers up here. And my most recent book is not a book, but it's this video series on how to architect distributed cloud applications. It's technology agnostic. So it's not about .NET or any programming language, and it's also not about Azure. It's just about how to put various pieces together for doing networking and messaging and queuing and load balancing and use proxies and partitioning and replicas and all of that stuff for building distributed apps. All those concepts are explained in this thing. And it's free and available at that link over there. So I highly encourage you to check that out. At the bottom is ways for you to contact me, my Microsoft.com email address. You're welcome to email me there. There's the LinkedIn thing, which doesn't work here. And I did look up why, right? It's because Russia wants data for Russian citizens to remain in your country. That was the explanation that I was told for why LinkedIn doesn't work here. And they don't have a data center here in Russia, apparently. And then at the far bottom is my Twitter handle, so you can follow me there. Okay, so that's me. So now we'll get into the hardcore of the topic. So first, this is a kind of a discussion about threading and about asynchronous programming. That's really what we're going to get into, and that's what we're going to use in order to build these responsive and scalable applications. Right? So if you go back to the early days of computing, the early operating systems, and if you're in the Windows or Microsoft ecosystem, that would mean like 16-bit DOS and 16-bit Windows, but it was true of other operating systems as well. These early operating systems didn't support threads. There was no such concept of a thread. Now, there was sort of a thread. We just didn't call it that. We would just say that there was one thread of execution that just ran through the entire machine. And the problem with these operating systems of years gone by was that when an application entered into a long-running task, which could be something like printing a document, or it could be some long mathematical calculation, or it could be you have a bug in your program that causes your program to enter into an infinite loop. Infinite loops are also long-running tasks. So when that would happen in the 16-bit Windows days, which I programmed 16-bit Windows many years ago, the whole machine would freeze. You couldn't do anything. Alt-Tab did not work. Control-Alt-Delete did not work. The only way that I, as an end user, could get control back of my machine was to literally power it off, power it back on, reboot, re-log in, and start doing everything all over again. If I had multiple applications running, like Word, PowerPoint, and Excel, and I had entered some data into them, but I had not yet saved it to disk, all that data I'd entered and not saved yet was lost. And I would have to retype all that stuff back in again. Needless to say, this was a horrible experience for end users. And Microsoft knew, and really specifically Bill Gates knew, back in the late 1980s we're talking about, early 1990s timeframe, that 16-bit Windows was not a good enough operating system to propel Microsoft into the future and be taken seriously as a serious operating system vendor. Bill also knew that within Microsoft, they didn't have the expertise. There was no employee there who really knew how to create a robust, reliable, secure operating system. So Bill looked outside, and he found David Cutler, who worked at Digital Equipment Corp., and he had worked on an operating system called VMS, the Virtual Memory System. And Dave Cutler had a bunch of people that worked with him on that, and Bill was able to make them an offer, and they all left DEC, and they came over to Microsoft. And they set them up in Building 2, which is being torn down like this year. I mean, imminently it's being torn down. And they're going to build a whole new building in its place. It's a little bit of history is going to vanish. But they set up a bunch of people in Building 2, and they were charged with designing for Microsoft a whole new operating system kernel that was going to be 32-bit operating system instead of 16-bit. It was going to use virtual memory. It was going to have security built in from the very beginning, network stacks built in from the very beginning, and it was going to have threads and process boundaries built in from the very beginning. And so Windows added this feature, which we now call today as a thread. And the purpose of threads was to make the operating system more robust and reliable for end users. A lot of times people think that threads make the system go faster, and that is not true. That's not their main purpose. The main purpose is for reliability and robustness. So what happened is when the user was using this new version of Windows, which is the same operating system kernel we have today and on my Surface right now, this Windows NT kernel, when the user creates a new process, they run an application that, like Calculator or Notepad, that creates a process. Each process gets its own virtual address space, so now memory was isolated between processes. That's really what you get with a process, is memory isolation. And then each process got one thread. And a thread, you can think of a process as a way of virtualizing the RAM, and you can think of a thread as a way of virtualizing the CPU. And then the operating system would take one process's thread, put it on the CPU, and now that application would run. And then a few milliseconds later, the operating system would switch that thread away from the CPU, take another process's thread, put it on the CPU, and let that one run. And now, if one application's code entered into an infinite loop or some long-running task, then the operating system would let that application's thread run, but only for a time quantum, we call it, a period of time. And once that period of time has expired, the operating system would preemptively, that means outside of application control, it would just do it. It would preemptively context switch away from the application that's in the infinite loop and put the thread from the other application on the CPU so that that application could make forward progress. And once the time quantum had expired again, it might schedule the thread to do a little bit more infinite loop, but then it would schedule this one back to make forward progress. And the beautiful thing about this was that if an application had its thread go into an infinite loop, it didn't steal the entire CPU forever. The operating system switched back and forth between the threads. This also meant that an end user, like you or me, we could go and hit Control-Alt-Delete, and we could bring up Task Manager, and we could go and kill the application that's in an infinite loop. Now that application would die, and any data that it had in memory that had not yet saved to disk, that data would be destroyed. But all the other applications like Word, PowerPoint, Excel, they would all continue running. And everything would be awesome, and the user would have a much better experience. The user would end up having a bad experience with the one application that's in an infinite loop, but would continue to have a good experience with the other applications, as opposed to the 16-bit Windows days where one application could screw up everything. All the other applications and the operating system itself, everything would be hosed. So that's really why threads were introduced into the system. And back in those days, it was very common for computers to have only one CPU in them. So if there's only one CPU, it can only run one thread at a time, and it context switches between them. Now today, of course, our computers have multiple CPUs in them. In fact, it's very hard to even buy a computer today that has only one CPU. Today, I think the Surface even has 4 logical processors on it. Even my phone in my pocket has more than one processor on it. And so today, if we are running on hardware that does have multiple CPUs, then the operating system can put one application's thread on one core, another application's thread on another core, and they can truly run in parallel. And that's how we get improved performance. So threads can give you improved performance only if you're on a multi-processor machine. On a single processor machine, they will not give you improved performance. They will make performance worse. And in the early days of Windows, we only had single processor machines, so they were really added as a way of adding more robustness into the system. As I mentioned, threads are a virtualization technology, and they are virtualizing the CPU that's in the machine. And as with all virtualization technologies, they come with some degree of overhead. And they have space and time overhead. Space meaning memory consumption, and time meaning execution time or performance. Whenever a thread is created in the system, the operating system has to create a data structure that represents the lifetime or management of that thread. And we call that the thread's kernel object. This kernel object data structure contains things like the thread's properties, the date and time when the thread was created. What's the priority of the thread? Is the thread currently running? Is it ready to run? Is it sleeping? What's the state of the thread? And so on. And then the most important part is the register set context. Sometimes we just call it the context for short of the thread. Now the context is a data structure, and it's the only data structure in the operating system that is CPU dependent. All other data structures are CPU agnostic. The context data structure has one field in it for each register that's on the host CPU. So if you were to look at an x86 CPU, for example, and you add up all the bytes required for the context structure, it's about 700 bytes of data. If you look at the x64 CPU and you add up all the bytes, it's about 1,240 bytes of data. And if you look at an ARM processor, it's about 350 bytes of data. Just to give you a sense of how big the kernel object is. It's at least this size, depending on the CPU architecture you're running on, plus some additional fields for other properties. In addition, every thread has a user mode data structure. Sometimes we call it the thread environment block, or the TEB for short. And this defaults to 4 kilobytes in size, and it contains things like the exception handling chain. That is, every time you enter a try block, a node is added to the head of a linked list so that if an exception is thrown, it can walk through the try blocks to find the catch blocks that might want to recover from this failure that's occurring. The head of that linked list is in the thread environment block. This also tells you why exception handling is always done on a per thread basis, right? A thread experiences an exception. That thread can go and recover from the exception. Other threads don't know about this exception happening at all. There's some other, the user mode data is also used for things like thread local storage, which in today's world is a horrible technology to use. So if you're not familiar with it, that's good. Okay? And you should try to avoid it. There's also some data in here that's used for the graphics device interface or open graphics library stuff in Windows as well. But the most significant piece of overhead that's involved in a thread being created, is the thread stack. And each thread really has 2 stacks. There's a user mode stack as well as a kernel mode stack. The user mode stack in .NET is 1 megabyte of committed memory. Actually, I think that's on a 32-bit system, and I think it's bigger than that on a 64-bit system. The size eludes me right now. And then there's a kernel mode stack, which is 12K on a 32-bit system and 24K on a 64-bit system. And so you need to say to yourself that whenever you create a thread, you are allocating memory for the kernel object, you're allocating memory for the thread environment block, and you're allocating these 2 stacks for the thread. So just creation of a thread comes with a lot of overhead in terms of memory allocation. Of course, all this memory has to be initialized too. That takes CPU time or execution time. And then Windows has this policy that I won't go into in a lot of detail, but when this was done for backward compatibility with 16-bit Windows, which when David Cutler and his people were designing Windows NT, this policy made a lot of sense for backward compatibility. But today, it's an unfortunate thing because it really hurts performance pretty dramatically. And the policy is that whenever a new thread is created in a process, Windows will take that new thread and will notify all the dynamic link libraries in the process that this new thread has been created. In the early days of Windows NT, it was common for processes to have maybe 5, 6, maybe even up to 10 dynamic link libraries in the process. So when a new thread is created, maybe up to 10 DLLs had to receive a notification. But today in Windows, you look at applications like Outlook, PowerPoint, Explorer, it is common for these applications to have more than 300 dynamic link libraries loaded into the process. So when a new thread is created, literally several hundred functions have to be called to let the DLLs know that the thread has been created before the thread's allowed to begin executing the work that it was created to do. So the point I'm trying to make with all of this is that threads have an enormous memory impact, and they also have an enormous performance impact of creating them and destroying them. Because destroying them, all this stuff has to be cleaned up. The next thing to realize is one CPU can only run one thread at a time. So as I mentioned before, the operating system puts a thread onto a CPU. It runs for time quantum, which is maybe in the order of 30 milliseconds or so. And then a context switch occurs where the operating system takes that thread off the CPU and puts another thread onto the CPU. And that's called a context switch. Every context switch requires that Windows perform the following actions. First, it has to take the state of the CPU registers, and it has to save them into that context structure for the thread that's being taken off of the CPU. And again, that's either about 700 bytes, 1240 bytes, or 350 bytes of data that have to be moved. Okay? Then the operating system has to take a little bit of time to look at all the threads that are available and choose the next one to go and schedule onto the CPU. So that takes some time. If that thread happens to be owned by another process, then the operating system has to switch the virtual address space. And so the cost, performance cost of the context switch goes much higher now. Then the system has to take the thread we're switching to, go to its context structure, and copy the bytes out of there into the actual CPU registers. So again, that means we're moving 700 bytes, 1240 bytes, 350 bytes. And then finally, now the CPU can start executing what this new thread wants it to do. Right? And that's what happens with a context switch. These context switches are happening approximately every 30 milliseconds or so in the system. And so this is a fair amount of overhead. Context switches are absolutely not for free. And this is one of the reasons why having more threads actually hurts performance. You're allocating all this additional memory, all this resources for it, and then if you have a lot of threads, there's context switching is happening all the time, and the context switches reduce the performance of the system overall. So all of this, what I'm talking about, is pure overhead, and it actually hurts performance of the system. So then you might ask the question, so why did Dave Cutler and his Windows NT people do all of this? And the answer is, it was required in order to provide end users like you and me a robust operating system, where one application, or really one thread, within an application could go into an infinite loop or some long-running task, but other threads are still able to make forward progress. And this change here is really what put Microsoft on the map. If this had not happened, none of you would be in this room right now. This was a huge, huge change. And it made Windows usable by a lot of consumers out there. And Microsoft wouldn't even be in existence anymore. It's a huge impact. So as software developers, what should you and I draw as conclusions from this discussion? Well, the first thing you should conclude is you should avoid threads as much as possible. Probably seems strange to come to a threading course or talk and it's going to be avoid threads as much as possible, but you should. And the reason why you should avoid them is because creating them, destroying them, incurs time and memory overhead. And we don't want to waste these things. But there is a corollary, and the corollary is we do want to use threads because that's what makes the system or your application be responsive. And if you happen to be running on a computer with multiple CPUs, then that's how you're going to get scalability. You'll put multiple threads on the cores, and they will run truly simultaneously, and that's how your application will get improved performance or better scalability. And so what this talk about is today is wrestling with this tension. How do we design our applications so that they use as few threads as possible, but the right number of threads so that we're gaining scalability and responsiveness? Okay, so To make it a little bit more concrete, we'll talk about I/O operations. Most applications are I/O bound. Actually, there's a little demo I can do for you. So if what we cared about most in the world was raw performance, right? We want to use the least amount of resources. We want to run as fast as possible. If we were on, let's say, a 4-processor machine, the ideal number of threads to have on the whole system would be 4, right? 1 per CPU, right? If we were on an 8-processor machine, then if we wanted the lowest amount of overhead and the best possible performance, then the ideal number of threads to have would be 8. 8. Here, I'll do 4 and 4. 8. Okay. And that way, if we don't have more threads than there are CPUs, then when the thread's quantum expires, the CPU will just continue to run the same thread, which means it doesn't have to context switch away and context switch back to it. It can just keep on running. And then we avoid the performance overhead of the context switch. Okay, so let's see how good we're doing. Here we are in Task Manager, and hopefully you can see these numbers. This machine has 1 socket on the motherboard. On that, there are 2 cores in that socket, and each core has 2 logical processors. I know that because the total number of logical processors are 4. So 2 times 2 would give us 4. So this machine has logically 4 processors on it, which means in an ideal world, if all we cared about was reduced resource consumption and highest performance, we should have no more than 4 threads on this machine. However, you'll notice I have slightly more than 4. Right? Closer to 2,420 or so, right? Instead. Now, we already know from this discussion that Windows wants to give each process 1 thread, because that way one process can't stop other processes from running completely. And so if we say that I have 218 processes on this machine, then you could maybe say, well, okay, that's going to explain why we have 218. So instead of the ideal 4, I can maybe rationalize 218. But instead, I have an order of magnitude more than that, so something must be wrong. And if we wanted to get more information, we could go to the Details tab here and right-click and turn on the Threads column. Where is that? Threads column here. And then we can sort these in descending order. And then we can see that the system has 174 threads. And by the way, if you look at the CPU usage column, we can tell that they are doing nothing. And you might ask yourself the question, does the system need to allocate 174 threads in order to do nothing? And the odds are the answer is no. We see Explorer has 78 threads doing nothing. We see that Teams, Microsoft Teams app, which I'm running here, has 57 threads. They're doing nothing. PowerPoint has 51 threads doing nothing. And you get the idea, right? So what we can say emphatically, without any doubt whatsoever, is all of these things are architected poorly. There's no question that's true. They're all wasting resources, and they're not using the resources. If the threads are not running, then there was no reason to have them. So this had gotten very bad up into and including the Vista timeframe, Windows Vista timeframe, by the way, where different teams at Microsoft were just creating threads like crazy and allocating all these memory resources, but then the threads weren't running or doing anything valuable. And then a lot of times people complain that Vista didn't run well on a lot of hardware devices. And then it was around the Windows 7 timeframe where Microsoft said, we have to fix this, especially if we want to run on small hardware devices like tablets. And so there was a big push within Microsoft to have all the teams work very hard at reducing their thread allocations inside their processes and really shrink it down quite a lot. That being said, I'm still at 2,460. So it can still get better than what it currently is. Oh, so the next thing I wanted to say is a thread is only ever doing one of 2 things. There's 2 possible things a thread could be doing. It's either blocked waiting for I/O, like a network operation to complete, or file data to come in, or for me to hit keys on the keyboard, or move the mouse, or touch the screen. These are all I/O events. Or the thread is running computation, right? It's adding numbers, it's moving data around, it's doing some kind of calculation, it's drawing on the screen, right? So a thread is either blocked on I/O or it is running doing computation. They're the only two possibilities. So now, if you see on my machine that I have 2,400 threads, but if you look at the CPU utilization, the CPU utilization is around 16 or 12%. So let's just call it 15% because it keeps changing dynamically. So that means that if the CPU is being used 15% of the time, that means that all 2,460 some threads are not running 85% of the time. That's what that means. They're not running 85% of the time. And then again, you have to ask, do I need this many threads to not do anything 85% of the time? The answer's got to be no. But this also tells us that of the 217 processes I have on my machine, are they mostly I/O bound or are they mostly compute bound? They're mostly I/O bound, right? They're 85% I/O bound and 15% compute bound. Most of the time, our applications are not running and they are blocked waiting for I/O of some sort. All right, so that brings me to the slide. So now let's talk about how I/O operations are performed. So in .NET, let's say you want to open a file on the disk and you want to read some data. So the way you would typically do that is first you would new up a file stream, and that's going to open a file on the disk over here. Then you would say file stream.read, and you pass in some arguments. I'm not showing those. And your thread, when it calls file stream.read, your thread calls the Windows function read file. It's a fully documented API. You should look it up and read about all the Windows nuances of it at some point in your life. What read file does internally is it allocates a data structure called an I/O request packet, or IRP for short. And this data structure is, I don't know, 60 bytes or maybe 100 bytes, something like that, just to give you an idea. And it has things in it like the handle of the file, the offset within the file where the read should begin, the number of bytes you wish to read, the offset of the byte array in the managed heap where those bytes should be placed when they're read, and maybe a few other pieces of information as well. But that gives you a sense of what's in this I/O request packet data structure. After the read file function, which is being executed by your thread, allocates this data structure and initializes it, then your thread jumps from user mode to kernel mode and comes down into the Windows I/O dispatcher code, and it passes the IRP down, where it is copied from the user mode stack onto the kernel mode stack. Now, the Windows I/O dispatcher, it sees for which device you're trying to do this I/O operation to. It could be a network request, or it could be to this DVD-ROM drive, but in this example, let's just say it's this hard disk over here. And so it goes and takes the IRP and dispatches it into this IRP queue. Every device has its own IRP queue. So now, I just changed the slides from their aspect ratio, and so that IRP thing is supposed to be in the queue on the left. Okay, slight screw up there. So then what happens is the device driver is going to pick up the IRP out of the queue, and it's going to hand it off to the hard disk, which in my example is going to throw it off the slide. Okay, but imagine everything was shifted a little bit to the left. Okay, so now the hard disk spins up, and it seeks the head to the right location, and it starts doing the I/O operation to read the bytes in off the disk. While the hard disk is doing this, what is your thread doing that queued up this IRP? And the answer is nothing. Your thread doesn't do I/O. Threads do not do I/O operations. Hardware devices do I/O operations. So your thread gets blocked. The operating system suspends your thread here, so it's not scheduled to a CPU. That's the good news. Your thread, while blocked, is never scheduled to a CPU. It's not runnable. It's in a non-runnable state. So it will never be context switched to. That's good. But it's just sitting in memory, right? All the tab and the kernel mode object and the user mode stack and the kernel mode stack, all that stuff remains allocated and initialized, but it can't be used in any way while your thread is blocked. Now, eventually, the hard disk, the hardware, will complete doing its work, and then your thread will wake back up, and it will return all the way up the call stack here, and finally, we will get back from the read call the number of bytes that were actually read into the buffer, and now you can go and process the data that's in the buffer. So this is how synchronous I/O works, and this is what most programmers do today. But Windows NT, Dave Cutler and his people, even back in the late 1980s, they had designed the operating system to support asynchronous I/O. And then there have been some improvements that have been done to it over the years. And if you want to build scalable applications where you're not creating lots of threads that just end up blocking all the time, then you want to perform your I/O operations asynchronously instead of synchronously. So let's walk through this example now. This is the good way of doing things. The previous slide was what many people do, but is not the efficient way of doing things. So now I'm going to new up a file stream similar to what I did before, but I'm going to pass in this special flag, file options asynchronous. This flag does two very important things. The first thing it does is it tells the operating system, Windows, not to block the thread that's requesting an I/O operation. So now our thread won't block when we request an I/O operation. The thread is allowed to keep running. That's awesome. We love that. The second thing it does is it puts the completed ERP into the thread pool. And we'll talk more about that very shortly. Now, once we've newed up the file stream with this flag, we can then call file stream read async. Read async internally calls the same read file function that I showed you before. And that function creates the same I/O request packet just like it did before. And then your thread jumps from user mode to kernel mode, passing the ERP down just like it did before. And now the I/O dispatcher sends the ERP off to the ERP queue, which is slightly askew, just like it was before on my slide. But now something different happens. Because we had used this flag over here, the operating system will not block my thread, and instead my thread is allowed to return all the way back up the call stack. And read async, which is the method that calls all this to happen, that method returns a task in .NET. And a task is an object that represents an operation that will complete in the future. And once you have this task, there's numerous things you can do on it. You can wait on it, so you could block a thread waiting for the task to complete, but of course we would highly discourage that because now your thread is blocked, and now you're wasting the thread's resources. You could call continue with on that task, which is sometimes a useful thing to do. Or in .NET 4.5, they added this ability where you can await the task. This await keyword in C# which expects a task on the right-hand side, it allows this thread that was executing the new and the call to read async, that thread, your thread, is now allowed to return back to its caller. Now, if this is a GUI application that we're doing this in, then that thread is the GUI thread, and the GUI thread can now return back to the message pump and continue processing user input events like keystrokes and mouse events, and that keeps the user interface alive and the application responsive to the user. And the user has a fantastic experience when working with your application. If this is not a GUI app, and then it's more likely to be a server app then, or it could be a console app too, but if it's a server app, then this was most likely a thread pool thread that did this in the first place, and so the thread pool thread simply returns back to the thread pool, which means that other things that are coming into the thread pool can simply reuse that thread, pull it out of the pool, and reuse it for doing other things. And I'll say more about that shortly. Okay, but now that ERP got queued up, and the device driver has to grab that ERP and send it off to the hard disk. So now the hard disk spins up again, the head seeks to the right location, it does the read operation to read the data into your byte array, and now when the I/O request is done, then number 2 happens here. The device driver will put the completed ERP into the thread pool. Again, this happens because we use this file options asynchronous flag. So now the completed ERP goes into the CLR's thread pool, which is over here. And what will happen next is some thread that's in the thread pool will wake up, grab this ERP, and call back into your code. And it calls back into your code right after this await operator, and it returns the result, which is the number of bytes that were read, same thing that file stream read would have returned. This returns that same integer, so now I know the number of bytes read, and the line of code below this can now go and process those bytes. One thing that's important to note is that one thread news up the file stream, that same thread calls read async, and then await allows that thread to return. Then the equals bytes read, that could be executed by a completely different thread. It might be the same thread, but it might be a completely different thread. It should not matter to you. Okay, you write code. Do you care which thread executes that code? Usually no, right? And if the answer is yes, I would question your design. Okay, you should design your code so that the answer to that is no. It should not matter which thread executes except in a GUI app where it always has to be the GUI thread that does UI stuff. Other than that one caveat, it shouldn't matter when you write code which thread goes and executes the code. Okay, so now we've done everything asynchronously and we have avoided blocking our threads. This slide, I'm not actually going to have enough time to talk through. I'm sure of it. So close your eyes for a second. Now let's go to this slide. Okay. So now let's see a slightly more complicated example. Here's an example of a function called issue client request async. And I'm passing in here the name of some server and some string message that I want to go and send to the server. Now, the communication technology that I'm using this example is name pipe client stream. So I happen to be using name pipes, but this is similar. You could do this with TCP or with other mechanisms as well. This was just the easiest one to choose. So in this example here, I'm newing up a name pipe client. I have the name of the server, which is a name pipe server. I don't show you that code, but imagine there's a name pipe server running somewhere on my network. And then I can pass in the name of the pipe. I pass in that this is a bidirectional pipe. None of this is that important, but this pipe options asynchronous is critically important. Right? This asynchronous flag does the same exact thing as the file options asynchronous flag. It says to the device driver, now it'll be the network device driver instead of the file system device driver. This will say to the network device driver that whenever a thread makes an I/O operation on this pipe, don't block that thread, let that thread return right away. It also says to the network device driver, when the I/O operation completes, go and notify the thread pool so another thread can come out and let our code know that the I/O operation has completed. Okay, so that flag is critically important. Then this is name pipe stuff, which I don't want to focus on, but I'm connecting to the pipe. I set the read mode. Here I'm taking the string message that I want to send to the server, and I'm converting it into a UTF-8 byte array over here, because I need to send bytes over the pipe, not a string over the pipe. And then we get to this line of code. Now I say pipe.write async, and I pass in the request and my byte array. So what write async does, of course, is it creates an I/O request packet. It sends it down to the network device driver and queues it up. Because we said pipe options asynchronous, our thread is allowed to return immediately, and we end up getting back from write async a task object. I can then await that task object, which allows the calling thread to return back to the caller. And again, if this was a GUI app, it goes back to the message pump to process more GUI events. If it's a thread pool thread, then it goes back to the thread pool so that that thread can come back out of the pool to go and do something else later on. When this data has been written to the server and the I/O request is then complete, the network device driver will queue the completeness to the completion port, the thread pool, which is built on top of I/O completion port. And then a thread pool thread will come out and it will continue execution of our code here at await. So now we know that the request has successfully been sent off to the service. Now my client code wants to wait for a response to come back. So I knew up a byte array of 1,000, which is where I'm going to put the response. I then, on the same pipe, I call read async to send an ERP down to the network driver to say I'm waiting for a read request now. And my thread comes back and returns back to me a task. I await the task, which allows this thread to go back to the GUI message pump or the thread pool. And then when the server eventually responds with a result, which could be 5 days from now, right? It would suck to have a thread stuck in the kernel for 5 days waiting for this response. But it's possible that maybe the server does some big computation that takes it 5 days. So now I didn't have a thread blocked on that. So when the server does finally respond with a response, the network device driver gets it, puts it in the thread pool, a thread pool thread comes out, returns from await with the number of bytes it read. I convert that byte array into a UTF-8 string, and I return it from this method, and then I close the pipe. Right, so this is showing doing multiple I/O operations within a single method, and it's talking about how the threads are not blocking during any of this, so that we can have a very small number of threads and we can just keep reusing them in our application over and over again. That reduces our resource consumption quite a bit and allows us to do all this processing using very few resources. In the framework class library, that's what FCL stands for there are a bunch of these async methods that have been added. They all return a task, and they all do basically the same thing that I've already described. They all create an I/O request packet. They all send it down to a device driver. The thread can return immediately, and then when the ERP completes, a thread pool thread will wake up and continue its execution. So on the stream class, which is the base class of all streams, file stream, network stream, and so on, you have read async, write async, flush async, and copy to async. Again, they all create an ERP, send it down to the driver, and do everything I've been repeating multiple times. Same is true for text reader and text writer. Any types that are derived from it inherit these async methods I show here. HTTP client, of course, which is a very popular class that people use all the time for calling out to REST services. I certainly use it a ton. It has get async, post async, and so on. It creates the ERP, sends it down to the network driver, everything I said. SQL command has a bunch of async methods on it, and tools like serviceutil.exe. These tools produce web service proxy classes. These proxy classes also have async methods on them to do the exact same thing that I have said numerous times. Okay, so why is this so useful? This slide here demonstrates how to create a non-scalable server. Why would you want to do that? You wouldn't. You want to do that. But this is what most people do by default. So now we're going to take a look at why this is problematic. What I show in this example are 3 different actors, if you will. Let's say I have 3 people using a browser. I picked the icon for Internet Explorer, but these can be any browsers anywhere in the world being used by any users. These 3 browsers are going to make a HTTP request to some server. So imagine that the server is ASP.NET, or maybe it's WCF. It doesn't matter what it is. Any kind of technology, the same thing will apply. And this server has a thread pool inside it, and we'll see how that gets used momentarily. And then when the HTTP request comes into the server, this is your canonical example for a website, by the way. The server typically then goes and makes a request to some other server, like SQL Server or some database, right? But replace this, you can replace these things with anything, it's all true, right? But this is just a canonical example. So let's say the first client makes a request. That request comes into the thread pool, and a thread pool thread wakes up and starts doing some processing, but then that thread needs to make a request down to this other server to go look up some data. If we make that request synchronously, which is the default, then our thread blocks there. So we've created that thread, but now it's not running, right? So it's just wasting resources. Then, if a second client request comes in, a new thread pool thread has to be created because the first one is busy. It's out of the pool. So a second thread pool thread gets created, it executes some code, then it needs to call down into the server, and when it does that, if it does that synchronously, then that second thread also blocks. And then, to make matters worse, if a third request comes in, the thread pool must create a third thread, because the first two are out of the pool and can't be used for anything else, they're just blocked. So now this third thread wakes up, it goes and executes some code, then it might make a synchronous call down to the server here, and so it blocks as well. So now I have lots of threads being created in this service here so that they can all stop running and be blocked. Right? It's a very inefficient use of resources. Now, to make matters worse still, if that server at the bottom, it might do all this processing in parallel, because maybe this is running on a multiprocessor machine or something, and then it can return the results back. And when those results all come back, all those threads wake up and they all start running. Now, if this is running on a machine with, let's say, 1 CPU or 2 CPUs on it, then we have 3 threads runnable on a machine that has only 1 or 2 CPUs. So that means context switching will be introduced, because the CPUs can't run all 3 of them at the same time. So it picks 2 of them, lets them run, then context switch one away to let the other one come on, then context switch that one away to let the other one come on, so that they're all capable of making forward progress, but now the performance is deteriorated because of the introduction of the context switching. And then, to make matters even worse, again, eventually, all these threads finish processing the result of the database lookup, and those threads all return back to the pool to return the results back to the clients. And now those threads in the pool, if they have nothing to do for a long period of time, they will kill themselves. And killing a thread is also a performance hit, because we have to clean up the user mode stack and the kernel mode stack and the tab and the kernel object and all that junk, notify all the DLLs in the process that the thread died with that thread, DLL thread detached notification. So there's a lot of overhead here, and it becomes very problematic. I did a demo. I have an app where I tested this. If this green process up here is a 32-bit process, you are able to create about 1,500 threads in here, and when you try to create the next one, it will throw an out-of-memory exception, which you cannot catch, and the whole process will crash in .NET. That's because each thread requires a megabyte of stack space, so that's going to be 1.5 gigabytes. You only get 2 gigabytes of usable space in here in a 32-bit process anyway. Some of that's used by the managed heap and other resources. So after you've created about 1,500 threads in here, you're done. So what that means is, if I had 1,500 browsers that all wanted to talk to my service simultaneously, well, if I had 1,501 browsers that wanted to talk to it simultaneously, then what would happen is the service would simply crash, and the clients would get no response. And then something would have to restart that service and try again, right? So it doesn't scale, right? This is not a scalable thing because of this. Okay, but now let's go and fix it. So we have the same actors here. And the first client makes a request to the thread pool. A thread pool thread wakes up and starts doing some processing, and now the thread pool thread wants to go and talk to the other server. But in this example, we're going to make this request asynchronously. So that means that thread won't block. So the thread pool thread gets to return back to the pool, so that when the second request comes in, the same thread pool thread can come out of the pool, make a request to the server, and then that thread can go back to the pool where it can be reused again for the third. So now I only have 1 thread in that green process there, and it has processed all 3 of these browser requests that are coming in. Now, because I made those requests to the SQL Server asynchronously, when SQL Server is done processing those requests, it sends the response back, and remember, the device driver is going to put those responses into the thread pool. So here we go, 1, 2, 3 responses into the thread pool. I work for months on these animations. I hope you appreciate these animations. Okay. And then the thread pool will grab one of those and execute it, and then send the response back, and then grab the next one, execute it, and send the response back, and then grab the third one, execute it, and send the response back. Okay. And this is now, so now if I have 1,501 browsers that all come into here, it works. It doesn't crash because I can use only one thread to do the whole thing. Now, if I happen to be running that green server on a dual processor machine, then the thread pool will have 2 threads in it. So then I can handle 2 at a time. Or if I put that green application on a machine with 8 CPUs, then the thread pool will have 8 threads in it. So then I can do 8 of them at a time. And the thread pool figures this out automatically and dynamically at runtime. When you boot your application, it sees how many CPUs are on the machine. The thread pool will have 1 thread per CPU. That is its goal that it strives for. It's not always true. In the previous example, I showed it wasn't true because we kept blocking them, so it had to keep creating more, even if you don't have as many CPUs. But if you don't block them and you do everything asynchronously, then the thread pool will really strive for 1 thread per CPU. And that way, you won't have any context switching. Because if it has only 8 threads, because you have 8 cores, and if 9 things get queued up, only the 8 of the threads will come out and run uncontended on the CPU, and then when one of them come back, it'll pick up the 9th item and go. So you get rid of all the resource overhead of creating the threads, destroying the threads, context switching between the threads. All of that goes away because we've made these calls asynchronously instead of synchronously. And that's the motivation for all of this. I don't have too much time left, but I think I'm doing reasonably well. So the next thing I want to talk about is application models and their threading models. .NET supports several different kinds of what we call application models. You can build console user interface applications with .NET. You can build NT services with .NET. You can build GUI apps like Windows Form or WPF with .NET. You can build ASP.NET web forms or web services with .NET. All of these application models come with their very own threading model. For console user interface or service application models, there actually is no threading model. Any thread can do anything at any time. Multiple threads can all call console write line simultaneously, and they will successfully write to the console. That works all great. For GUI applications, the window must be modified or manipulated by the thread that created it. This is a rule that is a requirement of GUI applications. When you want to manipulate a window, maybe like add an item to a list box, remove an item, put something into an edit control, something like that, the thread that created that GUI element has to be the thread that manipulates it in some way. If another thread tries to do it, it will not work. And for ASP.NET, there's a threading model where a client request coming into the service, it can impersonate the client's culture and or identity. Like English is spoken in the US, or their identity, which can be used for accessing resources on the server machine. And I have a link here for more information about that. So what Microsoft decided to do, I think this was around the .NET 2.0 timeframe, is they added a class to the framework class library called Synchronization Context. This is a base class. And then there's any team at Microsoft that builds an application model, right? It's like the WPF team, they build the WPF application model. The Windows Form teams, they build the Windows Forms application model. The ASP.NET team, they build the ASP.NET application model, and so on. Any team that builds an application model, they are required to create a class derived off of this base class, and this base class, or this derived class, basically it represents a connection between an application model and its threading model. It's like a level of indirection between an application model and its threading model. And the await operator in C#, when you say await in your source code, that causes the compiler to generate some extra code. And the code does the following. Before it allows your thread to return back to whoever called it, the await operator executes some code which captures the calling thread's synchronization context. There's one of these synchronization contexts derived a reference to a synchronization context-derived object that's associated with each thread. And the await operator captures that synchronization context object before it allows your thread to return back. And then, when the device driver puts the completed ERP in the thread pool, the thread pool thread wants to jump out and call back into your code. But it's not allowed to just call back into your code. It calls through the previously captured synchronization context in order to call back into your code. And what this means is, when you use await in your code, the right application model is being used for the application model that you're using. So another way to say it is, if you're building a GUI app, when you call await, a thread pool thread wants to call back into your code. But because of this mechanism here, that thread pool thread will actually tell the GUI thread to call back into your code. And this allows the GUI thread to go and update user interface elements successfully. Right, so you can like open a file, read some data, and then you want to put something into an edit control. Maybe the text that you read, you want to put into an edit control. Well, to update the edit control, the GUI thread has to do that. This ensures, this synchronization context mechanism that's built into await, ensures that the correct application model is being used. Okay, so for application code, this is usually awesome. You love it, and you get it for free. It just magically happens for you, and you are very happy. And for people who are building class library code, you hate this, and you despise it, and you wish that they hadn't done it. And I'll explain why. So here is a common problem that happens. This happens to be a WPF example, but similar examples exist for certainly for GUI application models, but also for other models too. Here's a case where I'm calling some async method, which is down below. So the GUI thread, let's just say the GUI thread calls this onActivated method. The GUI thread then initializes this URI variable. The GUI thread then calls HTTP length async and passes the URI variable into it. The GUI thread then calls this method. The GUI thread then news up an HTTP client and calls getString async. So the GUI thread creates an IO request packet and sends it down to the network device driver. GetString async then returns a task. We then await the task. But await is capturing the synchronization context for the GUI thread. So now that synchronization context has been captured, and then the GUI thread returns back up to here. Now in this case, we want to block the GUI thread until the IO operation is complete. This is usually strongly, strongly, strongly discouraged. But there are some times where you need to block on IO operations. So let's just imagine this is one of those times. And the proper way to do it is to call getAwait or getResult. I know some people call .result here. That is the wrong thing to do. The reason why that is the wrong thing to do is because if this fails and you say .result here, it will throw an aggregate exception. If you say getAwait or getResult and it fails, it will throw the actual exception that it is. So this is the correct thing to do. Calling .wait or .result is the wrong thing to do, but it's what many, many, many people do. So the GUI thread calls getResult, which now blocks the GUI thread. It is no longer able to run until we get the result, this integer that's going to come back from HTTP length async. Well, the network driver is going to pick up this ERP. The network driver is going to make the network request. The response is going to come back from wintellect.com. And now the network driver is going to tell the thread pool the IO operation is complete. The thread pool thread wants to come back out and execute this statement over here to sign the text into this text variable. But in order to come back out, it has to call through the captured synchronization context. And that captured one is the GUI one. So that the GUI synchronization context says, oh, I'm not going to let you do this. I'm going to go and tell the GUI thread that it should come and execute this. But the GUI thread is stuck here, and so it doesn't receive that notification. And now we have a deadlock. And your application is completely frozen and hung. at this point. And the user will have no choice, or you will have no choice, to open up Task Manager and to kill the process. And then you got to fix the bug and start all over again. And this is a bummer that it works like this, but it's also good that it works like this, right? So the problem is that for the GUI application developer here, this capturing of the GUI thing is exactly what you want. It's for the class library developer over here, let's imagine this is in a class library, that this capturing in the synchronization context is not what you want. Okay. So how do we fix this? If you are a class library developer, it is your responsibility to fix this. And you do that by calling this method configure await false. What that, on the task that is returned from getStringAsync, right, or on any task that's returned from some async method, you then go and call configure await false. And when you do that in your class library code, what you are saying is to the await operator, do not capture the calling synchronization context. I know I'm out of time. So this await will not capture the synchronization context. The thread will go back, the GUI thread will go back and call getResult. And then when the thread pool thread wants to come out, it wants to go and execute this equal statement, which it now can do because it's not going to call through the GUI synchronization context. So now this assignment is being executed by a thread pool thread, not the GUI thread. And then we return this length, which signals this task to be done. And that allows this code over here, the GUI thread, to now wake up, and now it can get the result, and it can continue processing. So to summarize, because I'm out of time, when should you call configure await false? This is a very common problem in .NET. And the answer is when you are building functions that are application model agnostic. Right? They're not tied to the GUI. Like, it could be called from any application model. Right? It's not tied to the GUI application model. It's not tied to ASP.NET. It's just a helper function that's useful in and of itself. Could be called by any different kind of application model. Then you should be calling configure await false on your awaits, and that will prevent deadlocks from happening. It also, by the way, improves performance, because capturing the synchronization context is not cheap. There's a cost to that. But if you say configure await false, it won't capture it, and so you'll actually get better performance, and you will reduce the chance of a deadlock happening in your application code. All right, and on that note, I'm already 5 minutes over, but I think I was practically done. That was another way to do it, and then I was done. Okay? So I'll go out and I'll take questions outside. Thank you for coming.
Thank you.